Matrix, welcome. Finally, it's your turn. I know that you guys, because you're good mindsetters, you've been watching grade 10 and 11, and now finally it's your turn. You already learned a lot, and now you are ready to learn more. Phil's with us today, and we will be chatting about
conservation of momentum. Matrix, stick around because this is a grade 11 topic. It's still examinable. Grade 11s, if you've covered this before and you want to watch for a little bit of revision, it's fantastic. But grade 12s, we're talking about conservation of momentum this evening. Stick around, send in those questions to Twitter, Facebook. We're going to be listening.
Yeah, so you mean the grade 11s can watch too? So those grade 11s walking away from their couches, they should come back?
Well, only if you've covered this section of work. We don't want to teach ahead of your teachers because that's going to make you annoying in class. But if you have covered this in class, some of the grade 11s already have, you can watch this.
Fantastic. So, we'll see you guys after the break. Welcome back, guys. I hope you're all ready for a fantastic show. I am. We're feeling energized from all the other shows before. Today, we are chatting about conservation of momentum. And I'm not going to be teaching you because I am behind the computer chatting to you guys. Follow us on facebook.com/learnextra. I'm here to chat to you. If there's any questions you want to know, just shout and I'll ask Phil. We'll ask your questions. Also on Twitter @LearnExtra. And it's also a nice way to keep in contact with us. But anyway, let's get straight to the lesson. Phil?
Thank you very much, Indy. Okay, conservation of momentum. Now, a lot of you may have forgotten this from last year. So grade 11s, if you're watching this and you're learning with us, fantastic. But grade 12s, this stuff is a little bit rusty. Biggest problem that I find when I'm marking matric papers or I'm taking a look through those tests or towards your prelim exams at the end of the year is I find that people have forgotten all about their grade 11 physics. Guys, this stuff is examinable. The really nice thing about momentum is that it's easy marks. I'm going to show you a couple of steps to try break it down and figure out how to get those maximum marks. We're going to start off by taking a look at just the definition of what momentum is. Now, very seldom do they actually ask you in an exam what momentum is, but it's purely for your understanding. If something has a lot of momentum, it has a large amount of motion. Now, a couple of ways that you can get a large amount of motion is either to go fast and gain velocity, or you can have mass. So objects can either have large mass, low velocity, or can have any combination in between. So if we take a look, the momentum is defined by its mass and its velocity. Something I want to make you aware of, and just to remind you, is that we're dealing with scalar and vector quantities all the way through matric physics. When we deal with momentum, it incorporates mass, which is a scalar, but because I multiply by velocity, velocity has a direction and an amount. So that means that velocity is a vector, and therefore momentum is a vector as well. This is the biggest downfall of matrics during their exams. They forget that momentum has a direction and therefore a sign. That's going to become quite obvious a little bit later on as we run through the slides. We reintroduce momentum. We try to see how it's conserved. All right, just remember that if you've got some questions, I want you to send us through to Indy. Take a look at Facebook, take a look at Twitter, send through those questions to us. We'd love to hear from you. So as I walk through these slides, I'm going to be getting feedback from you guys. In the ad breaks, I'm going to be uploading a couple of your questions and trying to answer some of them as you go.
Fantastic. Cool.
All right, well, let's get stuck into it. Now, momentum is usually broken up into two sections, and I'm not entirely sure why people insist on separating the two of them, but I like to start to talk about conservation because it's something which is very easy to understand. Conservation just means keeping something the same. So they very much like to ask you the law of conservation of momentum. So if momentum is being conserved, it means that it's staying the same, but you can't write that down in exams. There's big marks for your definitions for those level 1 and 2 sort of remembrance questions where they say, state the law of conservation which applies here. Well, the law of conservation momentum is to do with any time that you've got objects which come together in a collision or break apart. So that is any time that objects come together or come apart very often, the law of conservation of momentum applies. Now, anytime I've got conservation, as I said earlier, conservation means that I'm keeping something the same. So in this case, it's the amount of motion or momentum. Now, there's a couple of tricks to this definition, and I want to point them out to you as we go. Now, there's some really weird words inside here. I'm pretty sure Indy will agree. Okay, it sounds all sciencey, but we're going to explain our way through it. Where the marks are. The total linear momentum. Now, some words here which I don't use in everyday English, but I'm going to use them in my matric exam and get my 3 marks for this definition. The total linear momentum. Linear means that I'm working in a straight line. Sometimes, if I start dealing with momentum on a 3D scale, sometimes you will deal with momentum on 3D. Instead, we're dealing with just 2D inside high school science. If there's 3D, things get a little bit complicated. Okay, so when I'm dealing with my conservation momentum, it only applies when I've got an isolated system. Now, that's quite important. An isolated system, if you isolate yourself, it means that you're removed from everything. And this is no different. If I've got a linear momentum conservation inside an isolated system, I'm talking about a system which is free from external masses. It's also free from external sources of energy or force or anything like that. I'm hoping that this is clear for the viewers at home. I'm not sure. What are they saying on Twitter?
Let's have a look. Okay, well, Tumelo says, total linear of an isolated system remains constant in direction and magnitude.
Absolutely.
Well done, Tumelo. Okay, let's have a look. Tumelo, he says he can't wait for a challenge. He knows that, well, he said, we're doing revisions, so we want something that will challenge us on the paper. Not easy stuff, because momentum is totally easy. Well, you know what, Tumelo? Maybe there might be a mindset out there that might not understand, so we have to go through the basics. You know what? Tumelo, I'm waiting for a question from you. I better get a good question. I'm watching my time. In about 10 minutes, we'll be answering Tumelo's question that he's going to send through. Tato wants to know, what is momentum represented by the letter P?
Okay.
Are we jumping ahead?
No, absolutely. It's very, very relevant. When we start talking about momentum, we start talking about things. A lot of people are saying, why we use the letter P? Well, it's a limit that we've got. You've only got 26 letters of the alphabet, and most of the good ones are already taken. Now, why don't I represent momentum with the letter M? Well, that's already taken by mass. So what I'm going to do is I'm going to go back to our original formula. You can see that P I've used for momentum. The reason behind this is because I can't use a capital P that represents pressure that's already taken. Okay, so if I've got P in this case, M is taken up by mass. My velocity is V. So M and V do make a lot of sense. But over here, momentum taken up by P, very often they'll borrow from other languages like Greek or German. I'm not sure which is in the case here. I'll try to find out for the viewers. But basically, they've run out of letters in this case, and they've settled on the letter P. So if we try and figure out what's going on here, my momentum, my mass, and that's where the M comes in, my V for velocity. A couple of times we'll very often run into especially Greek letters and symbols which are derived from German words. I'm not sure what's happened here, but we'll try to find out for the viewers. Okay, now to deal with something that Tumelo said, something very, very good. Okay, the total linear momentum of an isolated system will remain the same. Now he added something to that, which is quite important. He's jumping the gun a bit, but he's introducing the next part. Okay, linear momentum includes direction and magnitude. Some of the viewers at home have picked up that momentum is a vector, meaning that it's got both amount or magnitude and direction. Now direction is the key to understanding momentum very nicely. He wants a challenge. I'm going to give him a challenge in just a moment. Okay.
Oh, good. That's what I like to hear.
Absolutely.
Okay? So Tumelo's going to get his challenge.
Well, absolutely. Okay, all right. We can think out the box here. We can throw a couple of questions around and see if Tumelo can keep up. Because momentum should be an easy section. We're going to work on getting it easy for the viewers at home. I'm going to take a look at just an object here. So I've drawn a very, very simple sort of dynamics trolley here with its 2 little wheels here. Very, very simple. It's got everything that I need for the momentum of this cart. It's got a velocity. It's got a mass. Now, one of the things that a lot of people don't actually remember to do when they're studying conservation or change of momentum is actually how to calculate the momentum of an object. I've got my mass, I've got my velocity, let's try to find the momentum. And what I've done is I've calculated it ahead of time. Something which I want to make people very, very aware of is that anytime I'm dealing with a vector situation, I've got to put in a direction. So one of the things that I'm just going to quickly slot in over here, and something that I want to get viewers at home used to, is that I'm meant to put in a direction indicator every time. We're lucky here. We've only got one direction. So something that I like to do is just to put in an arrow so that my examiner knows exactly which direction I consider to be positive. So off to the right on your screens is probably positive. and we've got our 5 kilograms that doesn't have a direction. Remember that's a scalar quantity. Let's find the momentum. Let's substitute it into our formula. That P is equal to M times V. Now, one of the things that I emphasized last time, on last Tuesday, was we were talking about science being a practicing subject. It's just like maths. So if I don't write this down, if I don't work it out for myself ahead of time, it's going to be lost. Pretty sure you'll agree.
Totally.
Okay, so what we're going to do is we're going to substitute our values, see what comes out. I'm going to pay attention to a few things when the answer does come out. So if I say that my momentum is equal to my mass multiplied by my velocity, I see that 5 and my 3 over there, just emphasizing my 3 is positive because I've chosen off to this side to be a positive direction. I see that I've got 15 kilograms from the mass, meters per second. Now they can and will take off marks if you're leaving out units on your answers. Please, I can't emphasize this enough. And I've got to mention a direction which is relevant to the question. I've said off to the right. Sometimes they'll give you compass bearings, sometimes they'll give you other cars or dynamics trolleys or solid objects to reference from. But in this case, I've just said off to the right because I've got no other reference for direction. Shall we continue?
Yeah, well, Lucky, he says, is it right to state the law of conservation of momentum this way? And then I think it is, in closed system, momentum after is equal to momentum after collision. Did that
Careful,
make sense?
he's left out a few very important bits there.
Okay.
So it says in a closed system, well, closed or isolated very often are used interchangeably. But he's got to mention that in a collision, the total linear, and they're looking for total and linear, those words get marks. Total linear momentum of a system must remain the same. So before and after can be the way that he says that. Now your examiners have got brains, they are science teachers, and very often they will be able to interpret your definition, but they're looking for keywords here.
Yeah.
Total linear momentum
Yeah.
must remain the same during a collision is what they're looking for.
Okay.
Are there any more questions of that sort of nature?
Let me have a look quick on the page. Sorry, mindset is... Okay, well, Quintine says, I wish I had Phil as my physics teacher. He's really good. But that's just to make you blush, really, while I'm looking for a question. Very funny producer. Okay, I think we should carry on, and as soon as I find a question, I'll let you know.
Well, what I've done is I've prepped a question before. Now, if you've got a pen and paper, matrix, even if you've studied this just as a challenge, what I want you to do is I want you to take a look at this example that I'm going to put up, and I want to see if you can keep up. Now, I'm going to break it down into bits and pieces to make sure that you understand the various parts that I'm going to be doing. In the next part, what I'm going to be doing is I'm going to be introducing a second object. I've got the first object traveling at its 3 meters per second, as we did in the last one, so it's got its own momentum. I've got a 5 kilogram as its mass that stayed the same. What about on the right? I've got another object which is approaching it at 2 meters per second. It's 6 kilograms. Now, the really weird thing is that a lot of people forget that if we think about a system, it's still made up of small little parts. I've got a part on the left, I've got a part on the right, I've got 2 objects. You can have as many objects as you like. I can have 5 objects all colliding at the same time, although it's quite unlikely unless you're on a highway and suddenly somebody stops and you get a multiple car pile-up. I hope that never happens to you at home or anywhere for that matter. But if I've got 2 objects colliding to each other and they're going to strike each other, we can start to predict what's going to happen after that collision. So what you've got to realize is that each object has got its own momentum. So I'm hoping that this point is being driven home to everyone at home. I've got a separate object and a separate object. I've got to calculate the momentum separately because they have their own vectors attached to them. A 5 kilogram traveling at 3 meters per second from the side and a 6 traveling at 2 in the opposite direction. You look like you've got a question ready there.
No, I don't actually.
Okay, no, that's absolutely
you see,
fine.
He likes to put me on the spot. I don't. I think I've got quite a few coming through. Guys, something I really want to ask you is please make sure that the questions are relevant. And that's not because we don't like answering your questions. We do. It's just so much easier if you keep sending questions in that are relevant to what we're talking about. We'll be able to get through so many questions. And that's all I have to say for now. We'll carry on.
Absolutely no problem. What I'm doing is I'm taking that as an indication that everyone's following through and people are actually working through this problem together. Most people have taken the cue that if I've got a mass and I've got a velocity, I can calculate a momentum. if I've got another mass, another velocity, I've got a separate momentum. And when they collide, we can start to see what's going to go on. And I've got an example just like that.
Perfect, because Bryce is saying, what is a real example of momentum?
Okay, real example of momentum. Bryce, if you're listening at home, and I hope that you're watching very, very studiously, and that you're following up everything that you've done in the day's work, and you're revising your grade 11 stuff, what I want you to see is that a real example of momentum is not constricted to something inside the lab. Very often collisions do happen. Anytime two objects come together, you can do this with your hands. Anytime you clap your hands together, you're conserving momentum. Anytime that objects come together or separate. So, I mean, you can even think about yourself jumping off the earth. There is a conservation of momentum example going on in practice. If you fall off your chair because you're so excited about science, I know it's a cheesy example, but I do it all the time, and I get really excited about this. And when objects come together or they come apart, I've got conservation of momentum in practice. You can do that either by... Sorry, you were saying?
It's amazing. So literally it's happening all the time.
Absolutely.
Everywhere you go.
Inside your body, you've got collisions happening between atoms. The way that you're thinking at the moment, you've got neurotransmitters colliding with synapses. I'm hoping that it's storing all this information, but even those are collisions. And biochemists study momentum down at a microscopic level, and they can actually predict what molecules are going to do because of their momentum and their speed. Now, we're going to go back to this question. What I'm going to be doing is I'm going to be giving the viewers at home that are thinking that they know it all, we're going to try an example. Most of you by the end of this should be able to handle this question, no problem whatsoever.
And I know that they're going to start shouting out answers, because I know mindset is out there and saying, oh, the answer is. So guys, while we're working through things, feel free to shout out the answer on the page.
Absolutely. Okay, one thing that I'd really strongly encourage you. It's widely known that learning happens in large groups, okay? And the internet is a great way to do it. I want you to put forward your answer, put it up on Facebook, and see what others are getting and discuss. If yours is different, try and figure out what went wrong, what went right.
Yeah.
Now, there's a lot to discuss on an example like this. What I'm going to do is I'm going to have two objects which are approaching each other. So I've again got my car on the left, which was 5 kilograms, 3 meters per second, heading towards the second car, which was 6 kilograms, heading in the opposite direction. If I take a look a few moments after my collision, I notice that my first car is moving off to the left with 1 meter per second after that collision. The question says, what is the final velocity and direction of my 6 kilogram object? Well, how do I even go about taking a look at this answer and breaking it down? Now, there's a lot of steps and a lot of marks which come into this, up to 7 marks for this particular question. Now, it depends on how they've broken it down and how they've scaffolded it. So what I want to do is I want to encourage viewers at home to try and work this out ahead of us. See if you get the same answer as us, and see if you're on the ball and you're following your directions and you're following what we're doing. So let's just emphasize our figures, let's collect our information and go forward. One object heading from the left, 3 meters per second and 5 kilograms. From the right, we've got another car approaching 6 kilograms, 2 meters per second. And then afterwards, my first object is seen running away from the scene of the crime at 1 meter per second off to the left. What happened to the other object? Conservation of momentum is going to tell us exactly what happened. But it's all about the approach. A lot of people say, I know how to do that in my sleep. The question is, can you get full marks in your exam because you know what you're doing? And we're going to show you exactly how to do that. Okay, so let's just give ourselves a little bit of space to work. And we're going to see how we actually start to scaffold a good answer. Now, a lot of people have this misconception, this belief that all they've got to do is give the right answer in the exam. Now, that's not what science is about. Science is about explaining what you know to somebody that is not sitting in front of you. And that's quite difficult. I find it quite difficult talking at the camera. I'm hoping that people at home are listening, and I'm hoping that this is coming through clearly. So I'm going to take a look at these steps and see what they are. Well, the first step always, and this is where they start putting a few marks to your name, is that I've actually got to show that I understand that the conservation momentum applies in this case. So I know that two objects came together. I must immediately identify, light bulb goes on upstairs, and I know that I've got to conserve the momentum. Okay, just a few other things that I've got to watch out for. A couple of things that people are not doing correctly and do differently from the way that I do it, and that's okay in some cases, and if you're not feeling sure about something, send through the question. Okay, one thing before we go anywhere, what is our chosen direction? Before I start anything in physics, okay, there are the 2Ds that I start off. One is a diagram, which luckily I've got behind me, and the other one is their direction. So one of the things that I've got to decide on my diagram, and remember to do this, the 2Ds at the beginning of every physics, mechanics, kinematics, doesn't matter. If you're talking about graphs, talking about equations, got to decide a direction because we're dealing with vectors here. Okay, so what I'm going to do is I'm going to go ahead and indicate what I think is going to be the positive direction. Now, a lot of people say, how do I decide? Well, you get quite smart about it, and the really great thing is that there is no wrong answer on choosing a positive direction. The reason behind that is whatever direction you choose to be positive, work with it, run with it, and interpret your answer accordingly. You can choose either left or right as your positive direction. A lot of people that contacted us earlier were talking about the heavier object always gets a positive direction. That's not necessarily the case. I can do a quick mental calculation and figure out which one has more momentum. 5 times 3 gets me 15, 2 times 6 gets me 12. The little guy's going to win in this case because he's moving faster. So what I'm going to do in this case is I'm going to choose off to the right as a positive direction. Now, I'm a little bit short on space here, but I'm going to indicate that nicely with a nice big arrow with a positive. Now, I'm going to emphasize this when I start my calculation. Okay, so let's see what the calculation might start looking like. Remember that I have 2 objects before, I have 2 objects afterwards. And the correct approach, and a lot of people are saying, well, do they give us this formula? No, they don't. And a lot of people are saying, oh, how am I meant to remember a formula with so many pieces? It's actually really easy. So what I've got to do is I've got to take a look at the pieces and see what they mean. If I've got m1, the first mass, times the first initial velocity, I'll multiply them together. All I'm doing is calculating the momentum like we did before. I've got a separate momentum right next to it. If I say m2, u2, that's the second object. So this is my momentum before of object 1, object 2. What about afterwards? If I've got mass of the first object and velocity of the first object, again, that's momentum. I know all of these pieces of information. And then the last one's got the goodie that I'm really after. I've got the second mass still, but I don't have its velocity. I'm not sure what you guys are doing. I'm not sure if the answers are coming through thick and heavy yet. I'm pretty sure that people...
We do have a few answers.
Okay.
Yeah,
all right. Well, let's see if we've done our maths correctly. I'm hoping that I've done my prep properly and that people are not way smarter than I.
Imagine if you get it wrong.
I'm hoping that I get it right. Okay. So let's see what our substitution looks like. There's a couple of things that I want to point out that are very, very vitally important. A couple of the things that you might notice is that I've got negatives which are substituted through. And that's what a lot of people are going to get wrong. I've got my first object at 5 kilograms multiplied by 3. Second object, which is 6 kilograms multiplied by negative 2. Now what I'm going to do is I'm going to go up to my diagram and see where this negative 2 came from. Now I can bet you a lot of you at home just said 6 multiplied by 2 without that negative. This is the single most common mistake that people make when they're doing conservation of momentum. It's all about the direction. I'm going to keep on saying it until people are sick and blue in the face.
Keep on saying it.
Okay, well, absolutely. So if I've got my momentum of my second object, I'm good to go. What about the momentum after the collision has taken place? I've got my 5 moving off to the left. Remember that I made left negative if right is positive. Let's just check my values before I go ahead. If I've got 5 multiplied by positive 3, let's actually put in some signs here. Let's just drive the point home. I've got a positive 3 over there. I've got a negative 2 because it's off to the left. And this, again, is the most important part. Afterwards, this guy's moving at a negative 1 meter per second because I decided that this direction was the positive 1. Okay, so if I've got all this piece of information, I do my substitution. Right, hopefully our working comes out correctly. So I've got my positive 15 from the earlier object, negative 12 from the next object, and I've got negative 5, which is left over in that other object, and I've got 6 times V2, which I'm hoping to work out. So hopefully you can see that if I've got negative 3 on this side, I take across the 5, that adds to give me 8. And if I simplify this, divide both sides by 6, what I'll get is an answer which I'm hoping that you can see. Right, I'm hoping that people can see this at home. I'm hoping that people are seeing something from this. Now there's something missing from this, and I want to ask the viewers at home to try and identify what is wrong with my final answer. There's something not quite right. Now, if my teacher tells me that, I immediately start going, there's something wrong, there's something missing. Either the number's not right, or there's units missing, or there's something else. Now, I'm not sure if anyone at home is starting to reply and is quick on the Twitter, but what I'm hoping that they can see is that my final velocity of my object, 1,33 meters per second, is a vector. please, 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 I must give in a direction. Now, I'm not going to say off to the right or off to the left yet. I'm going to drive home this point that I got a positive answer. Positive means that it's got a direction. Where was positive? Positive was off to the right. So I can now write in that I've got 1,33 meters per second in as my final answer there, but I'm not going to get my full marks. One of the things that I must remember to do is I must put on a direction. So what I'm going to say is that this object was traveling in that direction, but is now traveling in the opposite direction. So this, I'm just going to abbreviate, but I hope that everyone at home is going to follow when I say that it's in the opposite direction. So it's in the opposite direction to the original motion. Now, why not off to the right? Well, the problem with left and right, apart from the fact that most people don't actually know their left from their right, is that left and right are different to you and to me. So if I hold up my right hand, you're looking at the left part of the screen, and that doesn't work for an examiner. If they turn your page upside down, left and right swap places. So what you can say is that it's in the opposite direction to the original motion, and then everyone understands it. Because if it was moving in one direction and it reversed, everyone knows what I'm talking about. So opposite direction to the original motion is where it's going. I can see that Indy's furiously typing away there.
Well, I'm actually chatting to Lucky. I'm trying to keep my eyes peeled. I think he was the first person to get the right answer. Okay. He also did say to the right. So I'm just writing in opposite direction to the original motion.
Look, I mean, okay. In all possibilities, what's going to happen is your examiner has got a brain. They do understand what you're doing. But remember that your examiner is marking many exam questions. You want to make this as presentable, as good for your examiner as possible. You are trying to woo them to give you marks. That is your job.
Impress them.
Absolutely. Impress your examiners. Write neatly, set your work out nicely. Don't make it difficult to find your answer, please. Because it makes my job, especially at the marking at the end of the year, this is incredibly difficult.
Yeah. Well, now you know mindsetters. Hey? Guys, so many of you wrote in and gave us your answers. Well done to you guys. They got it right. And guys, they got it wrong. You know what? It doesn't matter, because this is how you learn. We're learning together. Right, Phil?
Absolutely, indeed. Now, one of the things that learners very often express in my class is they're scared of getting things wrong. And my opinion is if you're not doing things which are producing mistakes, or you're not getting things wrong, you're actually doing the wrong work.
And you're actually not learning either.
You're not challenging yourself. You're basically just doing exactly what you know. You're doing your ABCs over and over again, and you learned those back in grade 1. That's not challenging you. It's not stretching you out. It's not giving you anything to chew on. I'm not sure how we're doing for time. I think it might be close to time for a break. I'm not sure.
Yes, I think we should definitely have a break. I think, Phil, you've been talking for far too long. Guys, now that we're having a fantastic session, you've got that break, go and get some snacks. Bring me some too, I'm hungry. Anyway, see you after the break. Hi guys, welcome back. Glad the break was so short. Didn't even have time to run out quick. Guys, thank you. We've got so many questions. We're going to try and work through them one by one. I think we're going to start with Noxolo, the question I asked you before the break.
Okay, right. So Noxolo's asking a question about the mass. Now, this is something very confusing. She might have been watching the grade 11 show, and now we're doing physics, and we were doing maths in terms of chemistry. Now we're talking about maths in terms of physics. Now, when I write the letter M, this is a very, very confusing thing for most people. I say, okay, M stands for mass, and the problem is that when I deal with chemistry and I'm talking about moles, I deal with grams. Okay, now that's the really, really confusing things, because grams tells me something about chemistry in terms of moles. But when I deal with kilograms, the kilogram is a standard unit for physics. Okay, so when you're dealing with a physics paper, you're dealing with paper 1, I want you to put your physics cap on, and I want you to be dealing only in kilograms. Absolutely. I'm hoping that that is sorting out a lot of her problems, because she was a bit confused. Do I convert into grams? Do I convert into kilograms? Because very often, kilo is not the standard unit of something. And in chemistry, we do deal with grams of material. The reason that they've standardized it to grams over there is because we're dealing with molar amounts and grams per mole. However, in physics, we deal with kilograms all the time.
Yeah, I can imagine also the objects are bigger.
Well, in most cases, yes. I mean, sometimes it's tons and we're dealing with thousands of kilograms. If you were to describe the weight of a space shuttle, for instance, with 1 million moving parts inside there in grams, you're going to be very busy with lots of zeros. Were there any other questions to that sort of effect?
Okay, let's have a look. What if the two objects come from rest, then away from each other, like an explosion? Tato, I'm not quite sure if I understand. Phil,
I
do you?
do.
Oh, thank goodness, Phil.
Okay. All right. Well, Tato's posed a very, very good question. I'm going to give you guys a little bit of a challenge. What happens if the objects are actually stuck to each other? Now, Bryce asked a little bit earlier, what is a real-life example of two objects which are springing away from each other? Well, most of you don't blow things up on a daily basis. Okay, I'm hoping that you don't. And most of you don't shoot guns. Okay, I'm hoping that you never shoot a gun.
Ever.
But two objects which come apart really rapidly. Inside a gun, you've got a bullet. It's attached to the shell casing. It's attached to the outside of the gun. It comes out very, very rapidly. Both objects were still before. Now, a lot of people are saying, okay, well, how do I deal with a question like this? I've got two objects which are stationary before. There's no momentum. But then afterwards, we've got these objects which are flying apart from each other. How does all this momentum come into being? And it's in the science. So what we're going to do is we're going to try an example. I'm going to try something very simple, just with the carts. We're going to take two carts, and we're going to put a spring in between them and explode them in separate directions. I'm hoping that this is answering the question that's being asked.
I'm sure it will. Yeah.
Okay, so let's take a couple of carts. So I've got cart 1. It's come without its wheel. That's not very good. Right, so I've got cart 1. I'm going to make another cart and introduce its wheel as well. Okay, now what I'm going to do is I'm going to introduce a spring in between them. So let's just picture our spring. It's nice and tightly wound. It's coiled up between these two objects. And what I'm going to do is I'm going to shoot these objects away from each other. Now, one of the things that I want you to see is it's kind of boring if they're the same mass. They kind of look the same size, but let's give them different masses to be interesting. So what I'm going to do is I'm going to make the one on the left, because we haven't used 2 kilograms yet. Let's make that guy 2 kilograms. And let's make this one 3 kilograms. Okay, the question is, what is happening before the collision? I'm going to say that they are completely at rest. So we've got 0 meters per second. Now, I want you guys to follow this practice question at home. Even if you know what you're doing, this might spring a surprise. And if you're looking for a really challenging question, as I'm still waiting for that challenging question, I'm going to turn this into a horrible, mean question later on if you want me to. So I've got a 2 kilogram springing away from a 3 kilogram. Let's see what happens after our collision. Let's make a little bit of space. Let's work on this guy. So in all of these, a good indication that I've got a conservation of momentum question is that I've got before and I've got afterwards. Let's get ourselves 2 new trolleys and 2 new wheels to go with them and see what happens after the collision. So I've got my trolley off on the right and I've got my trolley off on the left, and you can see that they are moving apart from each other, and that's a really great indication that they've exploded away from each other. And let's just draw a spring. Our spring is now lying on the floor and things are moving apart from each other. I've got one object moving off to this direction. I've got the other object moving off in that direction. I need one of these velocities. So what I'm going to do is I'm going to give the velocity of this object after the collision. Before the collision, these two were joined as a 5 kilogram single object. Now that's going to come into play when we work this out. After the collision, I've got these 2 separate guys, all moving off in separate directions. I've got something flying off in one direction, something flying off in the other direction. You can do this experiment at home if you've got some rollerblades or a skateboard. Now, you'll need 2 of them, obviously, and you'll need 2 people. Now, the problem with this experiment is you can hurt yourself, so make sure that there's lots of space around you and that if you fall over, you're not going to hurt yourself. If you've got 2 objects of different masses and you push away from each other, what you'll find is that both of you will move outwards. Newton 3 does come into this. So let's deal with this object, let's deal with this object. Let's give this guy a velocity because we're very kind today. I'm going to give this guy a velocity of 2 meters per second off to the left. So I've got 2 meters per second off to the left. Before picture, after picture, good sign that I'm dealing with a conservation question. The question is, what happens to the 3 kilogram block after the collision, or after the explosion in this case? Where does it go? How fast does it go? I'm not entirely sure. Let's leave it up to the sums. Okay, So I've done the first of the 2Ds. I've got a diagram. I'm looking for a direction. Absolutely vital. Let's indicate our positive direction. I'm going to make it off to the right. Doesn't actually matter which direction is positive because it's not moving before. 2 and the 3 are moving at 0 before, and afterwards we're not entirely sure. I predict that the 3 is probably going to be moving off in this direction, and that's why I've chosen a positive direction here. But if you guys choose left, absolutely fine. We're not going to judge you. And one of the really cool things about Twitter is we don't know where you are. So
we won't come and find you.
Look, I mean, we have ways and means of finding people. So don't say anything nasty to each other or us. We will come and find you. We are science teachers. Okay, so I've got a 2 meter per second motion on my 2 kilogram object. Afterwards, we're trying to look for what happened to the 3. Well, first step. State your conservation momentum. Momentum has been conserved, or at least I hope it has, unless all physics is breaking down and the world is coming to an end. I'm going to say that my P before is equal to my P afterwards. Now you can say P initial if you want, so you can say PI and PA or P final if you like. So I'm just going to say that P before is equal to P after, and this should give my examiner an indication that I'm trying to conserve momentum. It's there before, it's there after, nothing has gone anywhere. Now, this is going to be slightly different to the question that we did earlier. Remember I said that every object that is separate has got its own momentum. Now, before they explode from each other, I want you to see that the 3 and the 2 are actually one object. The masses are added together. So, if they're all added together and they're actually physically linked together and they're moving at the same speed, you can consider them to be one object. So we're going to change the formula slightly. So remember that momentum is mass times its velocity. Which mass? Well, both of them. So m1 and m2, these guys work together with their initial velocity. Now some of you guys might not be using the letter U. You might be using V initial or VI.
I think there have been a few learners that have been discussing that on the page.
Absolutely. Okay, guys, you can use VI. And what I'm going to do, just to mix it up, instead of using U as an initial velocity, I can say VI. I'm also going to indicate on the other side VF. If I use VI, I've got to talk about my final velocity as VF. Okay, there's going to be 2 VFs. 2 separate objects, 2 separate momenta. One momentum, many momenta. Okay, so a little bit of an English lesson there, but we're dealing with 2 separate objects now. So I need 2 separate terms for their momentum. Okay, so if I've got m1 and it's got its final velocity plus m2 and it's got its final velocity, and I've got some of the information, all is going to be well with this. So what I'm going to do now is I'm just going to check to see if I've got everything that I need. This is my shopping list to solve this question. Have I got my first M? Yes, I do. It's 2 kilograms. Second mass, 3 kilograms, all's well. The initial velocity, 0. Makes my life easy because the mass is going to work out nicely. First mass, yes, I do have it. Its final velocity, also have it. Final mass of M2. Not going to change unless it goes on a diet, and as far as I know, trolleys don't go on diets. And my final velocity over here, that's what we're going to work out. There should only be one unknown, and then you're set to go. So let's substitute, let's see what we get, let's manipulate and find my final velocity and see if it is what we predict it is. If you're practicing enough, you're going to get a good feel for what the answers are going to be long before you get there. I'm expecting that I'm going to get a positive answer. I wonder if you can think why I'm expecting a positive answer. Well, the key is that I followed my own advice and I said that the positive direction would be off this direction. If the 3 is going in that direction, I'm hoping that it's a positive answer. Let's see what comes out. Well, let's substitute together, let's see what we get, and let's see if the maths are agreeing with my predictions. Okay, so if I've got M1, which was 2 kilograms, plus M2, which is 3 kilograms, multiplied by an initial velocity of 0, that's going to make that maths really easy. Okay, I've got my final mass here, which is 2. And one thing that I've got to remember is that my final velocity of this guy, if I'm following my own advice, and I'm going to mark it on there, is going to be negative. I bet you didn't do that. Lots of people have forgotten to put in this negative. For this answer, okay, well, let's see if I've got my negative over there. If I've got 2 times negative 2, has anyone got answers yet?
No answers coming through, but we do have a few mind setters on the page that are doing some incredible things.
Okay.
Mick Well done. He just said, guys, the reason why fill is combining the two masses and indicating the same velocity is because it's because this problem, they were a system before they exploded. So I think we're trying to say they were joined.
Okay, well, let's actually elaborate. Let's go with that. Okay, I'm all for mindsetters helping each other, and on Learn Extra, that's what we're doing. Okay.
Fantastic.
So the reason that I was combining these, yes, they are a system, but now I've got to be careful. Even though they're separate, they are still considered a system together. So what he's saying is that the system is all together in one mass, which is really great. I'm very, very grateful for the people helping out there, helping each other out. That's how we're going to progress.
Yeah, it's fantastic. I think it's so great. And then also there's Ngwako. He said, this situation is an inelastic collision. There'll be a combination of masses after the collision. Is that right?
We're going to get there.
Are we ruining things now?
No, not at all. I'm glad it's coming up because the concept of elastic and inelastic collisions is going to come up. I'm going to tell you now that this is an inelastic collision and he's right, but his reasoning's a little bit fuzzy and we're going to try clean it up and make sure that he gets his mark at the end of the year.
Okay, we'll get there a bit later.
Okay, so if I do my arithmetic, well, I've got 5 in the brackets multiplied by 0. I'm hoping that you know that this is 0. Now you're going to see the really, really strange thing coming out here. I've got my negative, and I'm hoping that you're getting -4 over there as well, and plus 3 times my final velocity over there. Now, if I take my 4 across to the other side, it does something really awesome. It turns into a positive number. Okay? So I've got 4, positive 4. Now, please, Matrix, you cannot just change sign because it doesn't agree with what you've done. If it doesn't come out as you expect...
Oh, you've just flicked something
up
there,
goodness,
Phil.
we've
I don't know
moved
where
things
it went.
around.
No, it literally just went up.
Oh, no, that's okay. We're going to bring it back.
There you go.
The wonder of the undo button. Okay, so I wish you guys had this in exams and you could do undo instead of typixing and scratching.
I know, can you imagine? If I hadn't said anything, you would have been like, where's the 0? It's gone.
Okay, no, well, absolutely. Okay, well, it's 0. It doesn't mean anything. Okay, so we've got 0 here is equal to -4 plus 3 times our final velocity. I've taken the 4 across. It's become positive. It's doing what it should. If it comes across as the wrong sign, don't just scratch out that sign because that means that you're losing marks somewhere else and you're losing a lot more marks than just your answer. Never change the sign just because it's a wrong sign or what you think it's meant to be. Please, go with what your equation says. The equation is right. Your substitution may be wrong. I want you to check. Be very careful. Okay, so we're nearly there. We're on the home stretch, and I'm hoping that people are furiously working this out, and they're way ahead of us.
Yeah, we are getting some answers.
Good.
We are.
It should be very familiar. Okay.
Sirian, Vakosi, Nokatula, Umila.
Okay, you guys are quick, okay? You're working it out, so if I've got 4 divided by 3 on the one side, that gets me a final velocity. So if I've got 4 divided by 3, that's going to give me 1 1/3. So if I've got 1 1/3, I've got 1,33, round to 2 decimal places. Are people getting this at home?
Mm-hmm.
Fantastic.
They are. Mbali, Miguel, well done.
Have they put in their directions?
They have. They said to the right, and then they've
Okay,
said
that's
to
fine.
the opposite direction.
Opposite direction of what? I've got to be very careful when I use these words in this language. Opposite direction to, well, I can say something at the end of that which makes it make a lot more sense. So I'm going to choose my direction very carefully. Something came out that made me very happy. It came out as an answer, which I expected it to, but it was positive. Well, remember what I said about positive earlier? Is that positive was off to the right, and that's where I expected the 3 kilogram to go. So if it came out plus, I predicted plus, things are looking good for me. Okay, so now some of them are saying in the opposite direction too, or they're saying off to the right. But now be very careful. Somebody said that we would never turn the page around.
Yes,
okay.
They said they didn't. They didn't say it like that. They said, Phil, who would change the page around? That just doesn't make any sense.
Okay.
And the answer was?
Okay, I definitely would. I'm one of those nasty teachers. I will turn things around just to mess with your perception. Okay, now never expect that everyone understands what you're trying to say because you've got to make it as simple and clear as possible. Off to the right, yeah, I'm not too keen on left and right because very often examiners, and you can't rely on them knowing their left from their right as well. It's a common problem. But that's not the reason that I'm trying to discourage it. It's because left and right is relative to the person. So my left and my right are different to your left and your right. It's not a universal direction. I can't say everybody go to the right. And I'm pretty sure a whole bunch of people just kind of shifted behind their screens at home. But if I shift to my right, I'm going to shift to your left. So if I step across this side to my right and your right are different things. I just want you to be very wary of the use of left and right. I would rather say away from the 2 kilogram. Everybody understands that these two objects are separating. That means that I'm in the opposite direction to the 3 kilogram. So that's a great way to state your case, to state your direction, and see what's going away. So I'm going to say away from 2 kilogram, and that is a universally understood. If they were together, the only way that away can mean is away from my 3 kilogram object. So I'm going to say away from either the other block, so away from the 3 kilogram block, and that is completely understood by everyone. And it sounds like viewers at home are managing to work through the questions and work with us, and that is fantastic.
They are. It is great.
Okay, well, I'm not sure how our time's looking. What are we doing for the last few minutes? Is there a question at home, or can I proceed with a really nasty one?
We have 10 minutes. Guys, do we do a really nasty one, or do we... Well, I do have actually... Okay, before we get to the really nasty one, we might have time for that. I've actually got from 2 different learners similar questions. Kolofelo says, can we do an example where a bullet goes into... Okay, well, there's one of them where a bullet goes into a piece of wood, and there's another one where a bullet goes in water. Let's maybe this one.
Okay.
I just hope that it is relevant. You know what, Phil?
It absolutely is. It absolutely is. I'll tell you straight if it's not.
Okay. Can we do an example where a bullet goes into a piece of wood and just stays there, and we have to get the VF of the wood, something like that?
Okay, no, absolutely.
And another question is, maybe, I don't know if you want to do this instead, is what happens when there are more than 2 objects? Because we've had quite a few questions on that, so perhaps that is a better one. Guys, I know I keep chopping and changing between questions, but I'm trying to figure out what everyone is asking on the page, and I think a lot of mindsetters are wondering what happens when there are more than 2.
Okay, well, the really awesome thing is, because there's so many online resources, is that long after the show has finished, people can use Facebook, they can use Twitter as a discussion board. So if they've got a particular question that they found somewhere on the web, they found the Siovula websites, the everythingscience.co.za, there are free textbooks, okay? They are absolutely free. You don't have to buy them. You can go find questions out there, and everybody has access to them. If you're sitting on Facebook, you can find free online textbooks, and you can discuss questions out of there, which is fantastic. And use these. And I'm pretty sure that once we start getting that going, what we can do is we can actually start pulling questions out of there, and everybody's got access to those. If you're watching DSTV and you're at a computer, you've got everything you need to get your A. So let's go with those questions. Which one would you like to do first?
Okay, let's start with... should we do the wood one first? Just because I read it out first and now I feel bad. Okay.
Absolutely no problem. What we're going to do is we're going to set up that question. I'm going to set you off in the right direction. What I'm going to do as well is I'm also going to discuss how we'd approach it if there were multiple objects arriving at the same place at the same time. Now, I'm not going to work through an entire question, but I'm going to set you up, push you in the right direction. Okay.
Fantastic.
So what we're going to do is we're going to need a block of wood, and very often a lot of people say either this block of wood is sliding along a surface, so let's get ourselves a nice surface, and very often it's not smooth because they want you to work out friction, all sorts of other nasty things. But tonight we're just dealing with momentum. So if I've got my wooden block and it's heading from left to right, and I'm going to make a very, very colorful bullet. Because we're working on black here, I want you to be able to see what I'm talking about. If I've got a bullet which is going to embed itself inside this block of wood, what's going to happen? If the strike's inside here, what's going to happen is if it goes through there, and this block is going to be traveling through there, and we've got this ginormous thing which is now traveling into a block of wood. Now, what happens as it strikes here and it's spinning through the air and as it beds itself inside the block of wood, what I want you to see is that it's going to add its momentum to the block of wood. Okay, let's give you a before scenario and an after scenario. Anytime that you've got a picture before and after, you've got a momentum question on your hands. Okay, so what I'm going to do is we're just going to deal with this all as one thing. Let's just move it. Don't you wish that you could do this at home? So what I'm going to do is I'm going to move this a little bit down. I'm going to move this a little bit down, give ourselves a little bit of space to work with, give the bullet a little bit of path. Let's trace its path over there, and let's move it inside there. All right, so we've got a bullet which is now striking it. I need a before picture. So I've got my same block of wood, and it's just resting there, it's relaxing, it's minding its own business. Along comes the bullet. We have separate objects before, we now have one object afterwards. Now, I'm going to help a lot of people at home set up their question, because a lot of people say, where do I start? It's always the problem in physics. I have no idea which equation to use and how to use it. Well, the really nice thing is that before and after. Before, I've got 2 objects. Afterwards, I've got 1 object. I'm going to call the bullet mass 1. I'm going to call the block mass 2. Not very imaginative, but it works. So mass 1 and mass 2 have added to each other. How do we go about this when we set this up? Well, now that we've got these all added together, so I need a little bit of space again. I'm going to set this up. So let's move all of this junk out of the way, all of the surface. Let's set up an equation together. So what do I do for the before? I state my P initial. That's right there. That P initial is equal to P final. A lot of people have said this. This is my conservation. P initial was separate objects. So M1, V initial 1. You can use U1. If you're using U and you're used to it, absolutely fine. Separate object, M2, V initial 2, and that's going to go to form one combined object. As somebody pointed out, I add together the masses if they're stuck together as a combined system, and then the final velocity of the whole thing together. If you follow this approach, you're going to be fine. What I'm going to do now is I'm going to spend a few minutes trying to answer what happens if 3 objects, or 4 objects, or 5 objects. Now, the key is actually in the way that I've approached this. Every separate object gets a momentum term. There's a momentum for my bullet. There's a momentum for the block. There's a momentum for them together. So if I was to take a look at this example, let's just copy this example and let's move further. What happens if I've got 3 objects all approaching each other? So let's have them a little different sizes. Let's have several objects. So what happens if I've got these 3 objects? So I'm going to have a big one, a small one, and they're all going to be approaching each other, and they all arrive at the same place at the same time. So if I give mass 1 a velocity over there, so let's call that V initial 1. Okay, what happens if this object was heading this direction? These could be cars heading from different directions. I hope this is never the case, but they could all arrive at the same place at the same time. Now, one of the things that you'll find out very quickly is that cars cannot occupy the same space. They're going to crash. Now, if they arrive at the same space at the same time, let's see what happens. So if I've got M3, let's make our M3 traveling very, very fast, just like the car, the M3. So if I've got V initial 3, notice how I've just said, okay, mass 1, mass 2, mass 3. I'm just trying to organize my information. What happens if they all smush up and they become one tangled mess of car and they start to move afterwards? And, well, we've still got mass 1, mass 2, and mass 3, except they're all together. Now, it really doesn't matter how many objects you've got. A lot of people have said, okay, well, here's a space rocket splitting into 3 pieces. The rule is, anytime you've got a separate object, you give it a momentum. And that's pretty easy. So what I'm going to do is I'm going to see how this equation is going to look. Again, you don't get this equation. The only one that you get is that momentum is equal to m times v, mass times volume. So if I've got momentum of 1 plus momentum of the second one plus momentum of the third one, I'm just going to say that this is my initial momentum. Now I'm just putting it out there. This is not the way that I actually start this question. So I'm saying that initially they are all on their own, and I'm going to call that momentum initial for each one of these. What I'm going to find is that afterwards I'm going to have a final momentum, which is for all 3 of them, because they are now one object, so one momentum. So if I've got momentum of 1 and 2 and 3 all together, let's see what that would actually look like if I followed this question, followed through.
Sure, we've got about a minute left.
Okay,
So
right.
We're
We'll
going to be able to do it.
Absolutely. We are that good. So M1, V initial 1, plus M2, V initial 2. Now you can see where this is going. M3, V initial 3. And now the magic comes afterwards. They have now joined onto each other, so it just becomes M1 plus M2 plus M3, all multiplied by that final velocity. And that's the way you're going to approach this. Looks complicated, not really. Momentum 1, momentum 2, momentum 3, all together as one at the end. I hope that answers the questions.
It does, and that's perfect timing full on it. Okay, guys, we have finished the lesson. I'm so sorry. We had such a fantastic time. Thank you so much, grade 12s, mindsetters. Don't forget, all of you that are watching grade 10s, 11s, and 12s, life sciences on tomorrow. Thank you so much for today. Bye, guys. Bye.